Eureka!
Archimedes' principle for the educated.
As demonstrated by the image, the force of gravity acting on the ball is less than or equal to the buoyant force pushing upward on the ball. Therefore, it floats. This is because the density of the ball is less than or equal to the density of the liquid surrounding it.
Will it flow?
Boat!
Here's our take on Archimedes' principle.
The equation for Archimedes' principle is best explained by using a generic cube as such, whereas the buoyant force is equal to the density of the cube, rho, times little g, which is the acceleration due to gravity, which in this case is 9.81 meters per second squared, times the height of the cube, times the cross-sectional area of the cube. But as you can see, if you multiply the cross-sectional area times the height of the cube, you get the volume of the cube. And since since the height is measured in, just for an example, measured in meters, times area measured in meters squared, you get volume equals meters cubed. Now if you take volume in units meters cubed times rho, which in this case I just said they were grams per meters cubed, you end up with a mass unit of the mass of the water displaced by the cube in grams. And therefore, what you have left over is if you replace V rho or HAV or HA rho, you end up with the force of buoyancy equals mass times the acceleration due to gravity.
Will it flow?
iPhone wrapped in an outer box.
We designed our experiment by placing a cup measured half full of water and then using a pill bottle to test the principle of buoyancy. We measured the rise in water level when the pill bottle was floating and completely submerged. Also notice that after being completely submerged, the rise in water level is non-existent. As you can see from the data, we took 3 trials to ensure accuracy, as well as our results correlate to the bottle being less dense than the water. In fact, if you look at the results below the table of data, you will notice all measurements used earlier when describing the equation of buoyancy.
Will it flow? Ice, baby.
It floats! From the great days of Christopher Columbus to the treacherous times of the Titanic. These ships are a true inspiration. Due to the massive size of ships in industry, such as transport vessels, their surface area is so massive that it allows the buoyant force to spread out evenly on the bottom of the vessel. This creates a greater upward force than downward force, allowing the ship to float.
Right, stop, collaborate, and listen.
Okay, we're testing the iPhone with the OtterBox into the water, and it doesn't float. Kind of an example, it's kind of surprising because you'd think otters would float. But anyway, yeah, now that my iPhone is kind of messed up, kind of an example. The reason it doesn't float though is because it's more dense than water, so it sinks. And just kind of an example of how it does take a little bit of thought to engineer something that does in fact float.
If there was a problem, yo, I'll solve it.
It floats. Bazinga!
Dude, didn't you know that water is the only compound that is less dense in its solid form than its liquid form?
Well, actually, to my gentlemen scholars, most of you know that ice actually does in fact float. But if it were not for that fact, our oceans would freeze over. Just by the simple fact that ice would freeze on top and then sink to the bottom, and in a continual process of freezing and sinking, our oceans would freeze solid.
It all started with the Big Bang Bang!
No, but seriously, if ice did not float, life would cease to exist.